Oh, wow. Following Mr. Consciousness himself. But I'm not going to give any percentages. AI consciousness is inevitable. Okay.
Yeah, go ahead. Lenore Blum from CMU.
Can you hear me? Everybody can hear me? Oh, thanks for all coming. Wow. And yeah, thanks to everybody who've organized it. Sherry, who's been wonderful, meeting all these great people in every different area. Okay, so this is a family affair. Manuel's been thinking about consciousness for a very, very, very long time, which I hope he'll tell you his story. I've been thinking about it maybe for 10 years, but started working on it more seriously here at Simon's in 2017, 2018, in Bruno's program of computer science in the brain. And then we were very lucky to have an in-house machine learning expert who we call on all the time. So that's been really, really great. Okay, so let me keep. Yeah, so this is definitely work in progress, and really would like to get a lot more input from people. But let me just what I'd like to say at the beginning is what I'm going to do to support our claim that AI consciousness is inevitable. And I really want to thank David for giving a lot of background, because a lot of things I say will fit into some of the things he's been talking about. So to support our claim, one is that we present a very, very simple formal machine model of consciousness, which we call the Conscious Turing Machine, that so it's a framework, and it's clearly buildable. And at a high level, it exhibits phenomena that's associated with human consciousness. And you heard about all these many, many theories of consciousness that there are. And so I've taken a number of them, and the CTM aligns and integrates many of the main theories of consciousness, which you've heard of. And that also suggests that these theories are probably more compatible than what people think, and are complementary. It's sort of like this proverbial elephant, and we're all looking at it from different angles, and they're all accurate, but there are different aspects, and some are probably more important than others for consciousness. And another thing, which I won't talk about it, but it's in our archive paper, we became aware that Kevin Mitchell, who actually got his PhD here, he's a neurogeneticist in Dublin, and he gave a list of 16 questions that and each question has 3 or 4 parts to it, and he said that any theory of consciousness should be able to address them. And in our paper, we go through, at least in terms of the CTM, we address those. So we thank Kevin Mitchell for that. Okay, so what is our goal? Well, we want something simple. We want something that we get our head around. We want something formal. We would like to have insights, at least for us and hopefully for others. And, I think a gold standard is to have some predictions, either that from the simple model have already happened, or things that we don't know that will happen and we're predicting. So here's my outline. I'm going to talk about the CTM. I'll give a brief introduction. I'm going to specify what it is not. I'll talk about its structure and its dynamics. We're going to talk about conscious attention in the CTM, and this is the consciousness that Dave had said was more like cognitive access or functional consciousness, but we'll also talk about feelings of consciousness in the CTM, and this is what Dave was focusing on, subjective phenomenological consciousness. So the first is often called the easy problem, attributed to Dave, and the second is really is sort of associated with the hard problem. And what's really interesting, and I'm really glad you said it, Dave, that the way you've posed the hard problem here is that it's almost a challenge to see how we could functionally create these subjective experiences. Many people have interpreted the hard problem as oh, that's something very different. It needs a new kind of science, a new kind of thing. But I think what you said here is what we look at it. It's a challenge to us to see how we can computationally sort of get something that seems like phenomenal consciousness. And then I'm going to talk about a line with a number of theories and conclude with AI consciousness inevitable. We also, in this paper, talk about how the CTM is also a good model for AGI, but I won't go into that here unless anybody asks. Okay, so the Conscious Turing Machine is inspired by Alan Turing's simple yet powerful model of computation. And here we have a 23-state universal Turing machine. This is in a book called Finite State Machines that I think Marvin wrote and came out in '68. And here's a picture of a 23-state universal Turing machine. You can get it way down. But anyway, that's sort of... but the idea about the Turing machine is it's a very, very simple model. But if you can compute something in the cloud or elsewhere, you could already compute it. And if it's computable in the cloud, it'll be computable in this Turing machine. It's very hard to get your head around the cloud or a supercomputer or LLMs or whatever. But you can get your head around the Turing machine and prove theorems or prove what can be computed, what cannot be computed. Okay, so we're looking for something like that for consciousness. And you've heard about the global workspace series. So we're also inspired by Bernard Barr's global workspace theory. And also Bernard Barr's, I think, did a lot of his early work here at Berkeley. And this is called the theater model. And so here's in the theater of consciousness. So let me tell you a little bit about the theater model. So Barrs describes conscious attention through a theater analogy. And he says that consciousness is the activity of actors in a play performing on a stage of working or short-term memory. The inner speech actor is often on stage. Their performance is under observation by a huge audience of powerful unconscious processes in long-term memory that are sitting in the dark. So here I am on stage, I'm the actor, and I'm sort of the conscious content, and I'm broadcasting to all of these unconscious, very powerful processes in the audience here. You're not in the dark. Well, maybe you're not in the, you have light here, but anyway, and at what Barr says is, so you're getting my broadcast, and Barr says that these conscious processors vie amongst themselves to get their script, query, information on stage to be broadcast to the audience, and we just saw that happen here. People were vying to get their questions on stage to be asked. So that's sort of the metaphor or the analogy that, so you're getting the broadcast. When you receive it, you're paying conscious attention to what I'm saying. Okay, so here's an example that I always like to give. You're at a party, you see someone you know, but for the life of you, you can't remember their name. Okay, what's their name? Has that happened to you? Then you drive home, and either on the way or when you get home, you remember her name when it's too late, right? So has that happened to anybody here? No, yes, okay. You don't want to admit it. Okay, so you recall when you first met, and maybe I met her here at the Simons Institute, and that's one processor, one of the processors is saying, I met her at the Simons Institute with a lot of weight, gets on stage and gets broadcast to everyone, and then another processor recalls from that what she does. Oh, she's interested in social interaction, social intelligence. And that gets up on stage, gets broadcast down. Another says, oh, her name begins with T, gets broadcast down. And about a half hour later, when you're home, the name Sherry comes to the stage from the audience of unconscious long-term memory processors, been thinking, searching. Now, first of all, you might note that T got up there, but her name was Sherry. And I'll address this problem later. But anyway, we know it's Sherry. So the conscious self on stage doesn't know how or where her name was or found. Okay, this conscious self is not privy to the workings of the unconscious self. And here's another direction of what I call the Poincaré effect, but it's like the aha effect. And actually, this story I read when I was a freshman in college. In those years, there was general courses and on creativity, and this is what Poincaré said. So Poincaré is a mathematician from the early in the last century, and he gives this story that he's working day and night on a very hard problem, can't get anywhere on it. And then he said, oh, so his friend called him up and said, let's go on a hike. And he said, that's great. He loves hiking. But then as he got on the bus, he says, as I was about to board a bus, the idea came to me without anything in my former thoughts seeming to have paved the way for it, that the transformations I had used to define the Fuchsian functions were identical to those non-Euclidean geometry. In other words, two areas that he actually knew very, very well. He really understood that they were isomorphic theories. So that's where these unconscious processes out here are doing a lot of work in the dark, talking to each other. And then when we're kind of relaxed, one of the processors sends its chunk up onto the stage. Aha, we have the aha moment. So that's the other aspect here. It's what's your name and this. Okay, so before I go ahead and tell you what the CTM is, I'm going to tell you what it is not. Okay, it is not a model of the brain. It's just a simple formal model, just like the Turing machine is not a model of the cloud or whatever. It's a simple formal machine model of consciousness. It considers the brain at a very high level of abstraction, at levels well above that of neurons and neuronal activity. So I'm above the fray. If you tell me it's not like the neurons that you know, neurons, whatever, okay. I'm not trying to look at the brain and neurons. I'm looking at certain kinds of functionalities. So the CTM is also not a standard Turing machine. It's not even a universal Turing machine. And what gives the CTM its feeling of consciousness is not its input-output map, not what's coming in, what's going out, nor its computing power, but what's under the hood, and it's dynamic. And that's our claim here. Because we're coming from a theoretical computer science perspective, what that adds to the Turing perspective is that we take resource limitations into account. Okay, so that's going to be an important feature of our model, and our model is actually finite. Okay, and then the CTM is not even a standard global workspace model. So the important difference is that we have a well-defined, so when Bars talks about the global workspace, he says the audience members just get together, decide what comes on stage. Well, if we have 10 million processors or more, that's not going to be a really good way to do things. So we have a well-defined competition process for global access. And in our model, Dave made an emphasis that the global workspace was a cognitive or access consciousness. CTM subjective feelings result from interactions between its evolving models of the world. Those are some of its processors and its global workspace. So this machine starts to evolve models of the world through its models of the world processor. And another big difference between a Bar's model and ours is that, I mean, we're formalized, he's not, but we have no central executive. He does talk about, stage director, and people also for organizations talk about CEOs. The model of our model has no central executive, and in fact, it's a feature, not a bug. It actually gives it more power to be a general AGI, more generally, and I could go into that, but it's in our paper. Okay, so now I'm going to give you the formal model, at least the high level. And so it starts off as a 7-tuple STM, LTM, uptree, downtree, links, input, output, and I'll tell you what this is. In our machine, time is measured in discrete clock ticks, t equals 0, 1, 2, up to, and we have a finite lifetime, let's say 10 to the 11th. It's born at time 0 and has a finite lifetime. STM is just a small memory capable of holding a single chunk, and I'll formally define chunk. Again, in the literature, chunk usually means a little bit of information, an idea, or something like that. We give it a formal definition. LTM is a massive collection of a large number, more than 10 million processors. That's what we're imagining in our machine. An uptree is a directed binary tree, and it's going to be the conduit for the competition to get the chunks on stage. The down tree will be the broadcast way of broadcasting. It's a tree that just broadcasts the winning chunk, down to the audience again. Links will be channels for transmitting information between processors. So one way of getting information is coming up onto stage, getting the information out. But after a while, our processes actually start non-linked. So it's like going into an audience when you don't know your neighbors yet. But as a while, when one processor answers the question of another, like the processor who said her name was Sherry, and the processor was querying what's her name, will start to link together. It's a kind of a Hebbian kind of system here. Okay. We have inputs from the outside world that go through sensors into the CTM, and outputs from special processors through actuators to affect the outside world. And the outside world we're looking at as real numbers. Okay, so what I'm going to do now is give you a sketch. I mean, I don't expect you to remember all of those things, but let me just draw a picture now of so this is our Conscious Turing Machine sketch. And here on top, we have a tiny short-term memory, which is our stage. And the stage can hold one chunk of information. So a chunk for us is a gist of information and a weight, a valence weight associated with it. I'll talk a little bit more technically in a minute, but basically that's what it is. And of course, it's not Miller's 7 plus or minus 2 chunks, which is what George Miller said is how much information we can hold in our memory, short-term memory at any moment in time. But we want to be simple, and we can get away with one chunk. So one chunk is going to do for us. Okay, and here on the bottom here, we have our audience of long-term memory processors. They're powerful. They're not connected at first. And their properties probably will emerge over time, though I will talk about actually building some in to start if we're going to build such a machine. Okay. Okay, so here's the input-output maps. So let me just say a little bit more about this. The input map is coming from the external world through sensors to specific processors that will be built into start. And the output maps are coming from special processors through actuators to act on the outside world. Okay. And what it's occurred to me, actually, and I'm sort of using this CTM-R because it's not a CTM is not a brain in the vat. It really has inputs from sensors and outputs to actuators, so it can affect the world. And that's going to be very important for the CTM of being conscious. Okay, so in our paper, we use CTM-R, but I'm going to go back to CTM because that was our original. Okay, so I'll say a few more words about the long-term memory processor. So processors are long-term memory processors. When I say processor, I mean long-term memory processors. Each has its own internal languages. Processors communicate within the CTM in a multimodal language, which we call brainish. Okay, it's a rich multimodal inner language. So the words in brainish really fuse images, sounds, sensations, like smells. Okay, so maybe a brainish word for a rose would combine the red color, the sweet smell, the soft touch of the leaves, and so forth in brainish. And Paul Yang, who's here, there's Paul, who just got his PhD at Carnegie Mellon, is developing a computer implementation for brainish. Who actually just got his degree, and he'll be on to MIT in the fall. So, touch with him. So think of a brainish phrase, which we call a gist, as a frame in a dream. So in a dream, you have a frame which has a vision, has sound, maybe some feelings, smells. I don't know if you have a sense of smell in your dream, but think of the brainish phrase as a frame in a dream. Okay, built into each processor is a sleeping expert's learning algorithm that adjusts weights. Processors give chunks based on feedback. So remember, the one processor said her name began with T, but was wrong. So when that processor sees that the winner says her name is Sherry, gets that. All the processors get the information. When that processor gets the information that was wrong, it's sleeping expert algorithm will say, hey, you were too bold with the weight you gave your answer. Cool it next time, so lower your weight. Okay. And then actually there was a processor who said her name began with S, but was not too sure. So didn't give enough weight, didn't get on stage, and it's a sleeping expert algorithm say, hey, you were right, boost the weight giving the next time around. So there's a kind of balancing act, and sort of maybe giving a little short shrift to Avrim's algorithms, but very important. The learning algorithms are very important in the CTM. Okay, and in the formal model, as I said, they're all the long-term memory processors are generic. There is some learning built in. And for now, or for we're thinking of building it, we can designate some important long-term memory processors, built-in model of world processor, and we'll allow off the shelf. Why not allow chat GPTs and all of that? So in this machine. We might put things that have biological functions like a visual cortex, hippocampus, thalamus, reticular formation, all of that. So one could do that. So one of the special processors might be your internal speech. Everybody talk to themselves. Not everybody, but many people do. That's important. But what's really important, I'll come back to this, is the model of the world processor. Okay, so now I'm going to go into a little detail on uptree competition. Again, this is for the CTM, but it has really nice properties. Where's my water? Okay. Okay, so at every moment in time, each long-term memory processors put a chunk into the leaves of its binary uptree. So that was the conduit. And now here's the formal definition of chunk. The formal definition, it's a four-tuple plus auxiliary information. So the four-tuple that's important here is the address of the processor putting in the chunk. And if like the 10 million processors, that could be just a 7-digit number, small number, the time the chunk was put in, the gist, a little bit of information that the processor's putting in Brainish. And again, it's delimited by, we want the uptree competition to be very fast, so we don't want to have too large amount of information there. A weight, which is a valence number. So it gets the importance or value of confidence that the processor gives its gist. It could be positive or negative, happy or sad type of things. And then the chunks compete locally, and the local winner moves up the tree one level. So it's like this. So you can think of it like a tennis tournament happening. All the processes they're paired together in this binary tree. They're competing locally, things go up. But, whoops, that's the important thing. Your chance of winning doesn't depend on your location in the tournament. So if you're in a very simple tennis tournament, if you're playing with somebody with a much higher rank, forget it. If you're playing with somebody with much lower rank, you're probably in good shape. In our competition, doesn't depend on where you're located. And that's really important because you don't want these processes to be moving around all the time. But where you compare with where your chunk and your value that you're giving to the chunk compares with the 10 million other chunks that are going on. And we have to do that pretty quickly, do that. Okay, so let me give you an indication of how we do that. So here I have two chunks that have moved up the tree a bit. And I want to know how they're going to compete and win, and who's going to win at the next level. So there we have C1 and C2 there. Okay, so here is what happened. At this stage, we had something that was fairly complicated. We had to have things like a decay mechanism and whatever. And we were determined to keep this thing totally deterministic. And we were trying to do that, but we couldn't. I mean, it was just getting too messy, and we're trying to be simple. So what we did here is now the model changes a bit and becomes somewhat probabilistic. And so the way we do this is we add to the uptree what we call a coin flip neuron. And the coin flip neuron just takes in two values, positive values, and then outputs the probability depending upon what those values are. It's a typical A. So for example, if we have C1 and C2, one thing we might want to do is look at their weights or the absolute value of their weights, put them in, and see what probability they get. With higher weight, we'll probably have higher probability, get to the next level, and so forth. So something like that's going to happen, but we don't do it at that exactly, because that actually isn't right. Okay, so we start with this will be our simple competition function, and the function will be what we call intensity. So at the beginning, all the chunks can have positive or negative weights, and now we're going to call the intensity the absolute value of the weight. Okay, and now we have a winner takes all mechanism. So what will happen is we look at the intensity of C1, we look at the intensity of C2, we plug them into our coin toss neuron, and one of those will come out with some probability. And the one that comes out with that probability, that will be the winning chunk with that probability. But now what we do is winner take all. The new chunk has the sum of the intensities. So its intensity will increase. So that's our winner takes all thing, which is what happens here. And let me give you an example with a simple tennis tournament and a simple CTM competition. So here I have on the left a tennis tournament, the right competition, CTM competition. I have 4 players, A, B, C, D. I have 4 chunks, A, B, C, D. I have the rankings of the tennis player. There are 3 that are ranked 1, 1 that's ranked 0. On the chunks, 3 have intensity 1. It's very similar. Okay, so now let's look at the tennis tournament. Where would you want to be if you have a ranking of 1? You would really like to be D, right? You can see that immediately, because immediately what's going to happen in the tennis tournament, you're going to, at the first level, you'll have a probability of winning 1, right? Probability of 1. Whereas A will have, A and B have the same ranking, so A's probability is 1/2. And then at that level, both of them have the same weight, so the probability of A winning at the next level will be 1/2. So we've multiplied 1/2 at the first level, 1/2 at the second level, so it's 4th. But B started with 1 and then 1/2, so it has a 1/2 winning. So A and B will have about 1/4 probability of winning, and D, of course, has the best probability. But now let's go over to the CTM and see how that works. So at the first level, you can see that, the probabilities are just like the others, right? The first level, the probability of A will be 1/2, and the probability of D will be 1. But now winner takes all. And so the intensity of A will be if A wins, the intensity will be 1 + 1. Well, at this level, actually, it's if A won, it takes 1 + 1. If D won, it only has 1 because C has 0. So at that level, now A has intensity 2 and D has intensity 1. Okay. But now at the next level, what's happening? So A has 1 + 1, which is intensity, over the sum, which is 1 + 1 + 0 + 1, okay? And D has 0 + 1. It's just intensity over 1 + 1 + 0 + 1. I'm just going through this thing. You can see those cancel out, and A and B both have the same probability of 1/3. Okay. Go through this, you see that the winner takes all is increasing. It's sort of like locally gathering global information. That's what's happening here. Okay. Hope that worked out. Okay. Any questions on the competition? Winner takes all. Okay. So I don't really know in simple tennis tournaments, while you're playing a game, somebody's ranking doesn't change while you're playing. It probably changes at the end of the thing. And then the whole thing, when you're playing again, there's a difference. But okay, so we have a range of uptree competition functions, and I just want to mention this one because it's really nice. It takes C times the intensity, that will be what you put into plus D times the mood. And when I said there was auxiliary information for the chunk level, at the base level, we will have we'll start with intensity weight, and we'll call something like mood the weight. So the mood starts with the same valence as the chunks weighed. Okay. So we can now have another intensity function which combines now competition function which combines intensity and mood. And this has a very nice property. And I just want to say, I'm not going to go through the calculations, but we say that if we use this, we say that the machine is level-headed if D is 0. That was the case we had before. If D is 0, we basically are looking at intensity. Optimistic if D is positive, and pessimistic if D is negative. And the extremes will say the CTM is manic if the D in this case is +1, and depressed if D is -1. And these definitions are not arbitrary because this D actually reflects CTM's disposition. It turns out that if D is positive, then positive valued valenced chunks will have more possibility of getting onto the stage than negatively valenced ones. And then the opposite, if D is negative valenced chunks will get on stage. And in the extreme, like if D is -1, what will happen is if there's one negative valenced chunk, no positive one will get on stage. The only way to get out of that situation is to reboot at that case. And that's sort of like a shock treatment. And we also looked at mania. You might think that that has the same situation, and it somewhat what does. And we looked at, to see if people were using shock treatment for mania. And it turns out that people haven't used it in the past because of onus of using shock treatment, and also shock treatment takes people out of depression. If somebody's manic, you don't want them to get more manic. But it turns out that the recent research shows that shock treatment can work for mania. So that's interesting. Okay, so when a chunk wins the competition and gets up into short-term memory, we call that, these are all formal definitions in the machine. We call that the conscious content at time t. And then there's the down tree, and the down tree will broadcast in one time unit that chunk. And by definition, we say conscious attention to CTM is the reception at time t+1 by all long-term memory processors of the broadcast of CTM's conscious content. So our formal definition is conscious attention in the CTM is when all the processes receive the broadcast. That's when you're paying conscious attention. Okay, and there's a little bit of limit in here too, because it takes some time for the chunk competition. Not a lot of time, but if we do the timing right, it's like 200 milliseconds to get up to, for the winner to get into the short-term memory, and then to be broadcast 1 more second or 1 more millisecond or something like that. So there's a little bit of that. And so all of a sudden we can see there are cycles of what we call predictive dynamics in this machine. It's all over, but right away we can see when the processors are putting chunks into the competition, you can think of those chunks. It could be a query, it could be information, but you can think of it as a prediction. I predict her name starts with T, for example. Then that goes in, and then when we have the broadcast, all the processes are getting feedback on that. So you can think of that as feedback. And then the built-in learning algorithms will help change the dynamic again for the processors. So globally right now, you can see a lot of what we call predictive dynamics going on in the machine. Of course, then you can look at when processors are giving information to the outside world and things are happening and they're getting feedback that way. There's more kind of dynamics going on as well. So up till now, I haven't talked about links. And links are interesting. As I said, that the processor that said, what's her name, will link up with the processor that said her name is Sherry. And what that does is what the links do is it changes all the conscious communication, which has to go through short-term memory. Everything has to go through the stage at first, that we're able now to quickly communicate through people in the audience in the long-term memory. And so, for example, when you're learning to ride a bike, everything you're doing has to be kind of conscious, but after a while the links form and then you ride your bike. unconsciously, except if you hit some pedestrian or whatever, then things go back to going through short-term memory. And the Poincaré effect is a little like that as well. There's a lot of work going on down here through links, communicating about all the mathematics, and the aha moment is when one processor decides, oh, I have the answer, I'll put a lot of weight on it, it'll get up to short-term memory and be broadcast. So that was the opposite. Oh yeah, so Allison always said something that for me was very, very puzzling. She said babies are more conscious than adults, and I really couldn't understand that at all. But I can see in the CTM how that is true. So baby CTMs are more conscious than adults with respect to conscious attention, because at the beginning, all the information is going through short-term memory. We're paying conscious attention when it's broadcast. A lot of things are happening before the links start to develop in our CTM. So at least in our CTM babies are more conscious with respect to conscious attention. But attention is not all you need. Okay, just we'll say that. Okay, so what do you need? So why would a robot with a CTM brain feel conscious? And so we're going now into the domain of the hard problem. Okay. So where are we now? Okay, so for us, the ability to create and utilize world models in the CTMs is very key to its feeling of consciousness. Okay, so in the CTM, we have a model of world processor. Actually, it's a collection of processors, and Manuel's even conjecturing it's all processors act as the model of world. And this processor is linked to and interacts with many processes, other processors. So let's see how the model of the world works. We have the model of the world out here, and there's a model of my CTM's model of the world. And it has an inner world and an outer world in its model of the world. And so the model of the world processor takes models of the world and the CTM in these worlds. The processor serves many purposes. It figures in exploration and in planning. It's how the CTM understands itself and the place in the world. It makes predictions and updates given feedback. It tags. So what's important here is it tags elements in its various models of the world with multimodal brainish gists, including labeling actuators as self when it consistently detects them carrying out its requests. So it starts to have notions of self and not self as it's developing. And let me give you an example here. So there's always the obligatory baby in this conference. Everybody has a baby. Here's my baby picture. So the baby model of the world is really just a fog at the beginning. Maybe the mom starts to get more pronounced in its model of the world, and maybe the bottle. But let's see what's happening with this particular baby.
And they move.
You see what's happening? This baby is discovering its leg, and it's sort of seeing from power of thought it can move its left leg. And in fact, it tries to see if it can do the other leg. And I think maybe it's a left-handed kid, but hasn't quite done that yet. But it's labeling, then it's really discovering that's self. And that's how the baby's model of the world starts building up with brainish labels more and more and gets more developed. Okay, and here's another example when the model of world processor dissects CTM paying a conscious attention to brainish labeled sketches of the rows. It tags CTM as consciously aware of the rows. So when we're saying that conscious awareness is when we have multimodal labels of these sketches. So when I have a rose and my model of the world labels it with the sweet smell, the bright color, the soft touch, I now have a feeling of, that's a multimodal word. When that gets broadcast by attention, then I'm more consciously aware of that. So it's an amplifier of consciousness, not just conscious attention, but it's conscious attention of a brainish labeled, rich brainish labeled gist. Okay, so that's our definition. So it'll say that it's consciously aware of that. It'll label that. Now I'm consciously aware of that rose, project that down. Okay, so our definition now of conscious awareness, it's attention, conscious attention of brainish labeled model of the world sketches. So we had conscious attention, now this is modified conscious attention. Okay, and then when the model of the world processor detects that the CTM thinking about its own consciousness, it tags the CTM and its models as conscious. Okay, and now let's looking at the CTM from the viewpoint of the outside world. We see that something about the CTM is conscious. Specifically, the CTM considers itself conscious. But what is conscious cannot be the model of the world processor or any other processor. Those processors have no feelings. They are just machines running algorithms. So we propose the view that the CTM as a whole feels it is conscious is a consequence in part of the fact that the model of world processors views itself in its models of the world as conscious, and that view is broadcast to all processors, in particular broadcast to processors associated with feelings of consciousness. And this is kindred in spirit to Michael Graziano's, which you heard about, attention schema theory. It may be a little different, but very similar. It's also kindred in spirit to Dan Dennett's view of consciousness, that consciousness is the brain's interface with itself. So it's part of a genre of views that are consistent with this. I don't know if they're exactly the same, because we're bringing in this very rich labeled brainish vocabulary. So, but to understand this a little bit, it often helps to look at pathologies. So Cotard's syndrome is a syndrome when people think they're dead. And that's because in their model of the world, somehow they've labeled themselves as dead. Body integrity identity disorder is when someone has a limb, it's perfectly good working, but they don't feel it's part of self. And they go to doctors in the US and they try to have that limb removed, and nobody here will do it. They'll go to Mexico and have the limb removed, come back in crutches or in a wheelchair and feel great. Okay. And then something similar to that is phantom limb syndrome, where you've had a limb cut. It's no longer there, but it's still labeled self. And so you may need to scratch it, may feel painful on that. And delusional paranoia, your best friend is a CIA agent. Had a problem with that at one time. Somebody in the audience thought I was a CIA agent. Sorry. Okay. So the reasonable of the model, yes, Umesh.
Consciousness. It seems like being conscious of being conscious is an essential.
Yeah.
It sounds like being conscious of being conscious is an essential element. So would this apply to animals as well?
Okay. So everybody, often people in our computation theory bring up the recursiveness. And what's happened, I may answer a different question that you've asked, but it's related, so I'm going to answer my question. Okay, and there's this notion of recursiveness, like you have the model of the world, which has the model of yourself, and inside your model of the world, no, that's not what you're asking. But
what you said, in your explanation for why the CTM is conscious, it seemed to invoke the fact that it was conscious of being conscious.
It's conscious of being conscious. That happens to be probably related to a higher order theory, which Megan, I'm not sure if it's true, but in a few seconds, if I have some time, I'll relate to other theories of consciousness. That's one theory I don't know very much about, so I haven't related it to that, but I'm really eager to hear your talk to see what that is. But we'll talk about that offline. Okay, so we have gone through a whole bunch of things that are in psychology books that people identify with consciousness, and we wanted to see if the CTM could experience that, and we went through a whole bunch, and I'm going to give you and the explanations often at least align at the high level with some of the neuroscience literature. So blindside is this case where people feel they're blind, but they can maneuver. And this is an extreme case of blindsidedness. And the man is asked to go to the other room, or the CTM, and he says, but I can't see. And nevertheless, he gets up, walks to the door, avoiding obstacles. What's going on? So I'm going to give you a CTM, very simple explanation. But I'm going to assume that this CTM already had sight. So actually it had formed connections earlier on, and then sort of got bumped on the head or something, and then became blindsided, or something happened to cause the blindsided. So what's happening is information is coming in through the sensor of the eye to the vision processor, which may and may not be working properly, but it also has links already formed to the motor processor. Okay, so it sends message to the motor processor to walk, and so the guy starts walking, but the connection from the vision processor is broken, either because the vision processor is not working that well, or that connection to the up tree is not there, or broke, or something. So because the information is not getting up to short-term memory, it's not being broadcast. So in our model, the CTM doesn't have the conscious experience, the conscious attention that it can see here. So that's our explanation in the CTM, and it does align with several of the theories that we have looked at. So I'm making a prediction in humans that blind sight, real strong blind sight, requires prior sight to have made these connections. May and may not be true. And I want to just talk about something called change blindness, because this is also indicative of GIS. So you may have seen this video. This detective comes into the room. He sees a dead guy on the floor, and then he says, clearly somebody in this room murdered Lord Smythe. Each of you tell me your whereabouts. And he goes to the maid, and she says, I was polishing the brass in the master bedroom. And the butler said, I was buttering his lordship's scones. And Lady Smythe says, I was planting my petunias in the potting shed. And then, of course, the detective's very smart, clever. Constable arrests Lady Smythe. And she says, but how did you know? And then he says, Madam, as any horticulture will tell you, one does not plant petunias until May. Okay, but for us, the big mystery is, why didn't we see what was going on? Why didn't the CTM, or why didn't we see the many changes? You can see the detective, his coat's gone from dark to white. The dead guy's knee is off the floor. He's obviously changed clothes also. Flowers have changed. All sorts of artifacts around this room have changed. Okay, so what's going on? Okay. So detecting change in the whodunit video would have required significant changes in the gist describing the beginning and ending scenes, okay? But size limitations on conscious content and the clever scene transitions by the director cause the high-level description to be essentially the same. We have the same gist explaining the first scene and the last scene. The scene is the living room of a mansion with a butler, maid, and detective, and a man laid out on the floor. Describes both, and that's what we've kept in our. So CTM can experience change blindness because of the limitations of its gist size. Okay. Okay, and that also. Okay, so I want to now quickly end with going alignment with other theories. As you know, there are many theories, and oh yeah, last summer Dave won a 25-year-old bet with Christoph Koch that Christoph Koch would have solved the consciousness problem by now, and he hasn't. So you got a wonderful case of wine. And there's been a lot of feud by all these different theories. What's going on? Okay, I won't go into all, but here is a sort of the listing of many of the major theories, and I want to just quickly go through them. We've heard about the global workspace, and we've heard about attention schema, and of course those two align with our model very much. Built in is a global workspace, and we have a model of the world that acts like this. Predictive processing, very big theory. Prediction is very important, predictive dynamics, but we have predictive dynamics in world models also in the CTM. So there are the 3 E's, actually there's 4 E's, embodied, embedded, extended mind theory. So the embodied means where our body affects our consciousness. Well, the CTM has sensors and actuators. It's embedded in the real world. It interacts with the outer world. In acts is the 4th E. And extended mind, which is a theory that Dave and Clark proposed, that we all had libraries at that time. Now we have ChatGPT and all those things. So we're allowing off-the-shelf processors. IIT, which was mentioned as one of the mathematical theories. Well, core to IIT, it's a measurement of consciousness, but there are two fundamental things about it. It says there's a lot of feedback, and it says there's a lot of integration. Well, the CTM has a lot of feedback, and it's integrated through the global workspace and all through the brainish fusion of sensory words. There's another theory that Mark Sohm says that consciousness starts at the brain stem here and then emanates up. Well, there's nothing to preclude the CTM for having processes that are like the extended reticular formation there. So that's and Friston has a free energy principle, which talks about what one tries to do is minimize the free energy, and he talks about internal states, external states, and divided by a Markov blanket. But if you flip that picture around, our CTM has internal states, external states, and it divided by a Markov blanket of the sensory and the actuator states. So we also have that kind of picture. And then evolutionary theories of consciousness. So Oren Zaks and Eva Jablonka talk about the evolution of the global workspace in vertebrates. Okay, so we have a global workspace, and in this conference, people talk about nature, so that was already put in, nature. But then Nick Humphrey talks about the evolution of the model of the world in warm-blooded animals. He talks about, and he has a chapter, chapter 12, called The Road Taken, where he shows sort of how this evolution would have happened. And what I did as an exercise, I rewrote his chapter with the CTM instead of his example, and I sent it to him, and he was okay with that too. So that might be called the nurture part. So the evolution in terms of how the long-term memory processes will evolve over time. And so my summary conclusion, we have a simple model. It's clearly buildable. It is a phenomena associated with human consciousness. It aligns and integrates with many of the theories of consciousness, and AI consciousness inevitable. And I have a 3-minute film, which I'd really like to show now. So this is an interview with Warren McCulloch in 1962. And I put a warning on the film. And I got it from Yevgeny Morozov. And this is, we knew Warren a lot, but I never saw this before last week. So I'll let you see it too. Okay.
No, I would expect that insofar as machines might survive man, they might, they would only carry on, in a sense, the same direction, same general direction, that man would have carried on if he could have. Am I clear? So to speak, the machines would be standing on our shoulders.
Somehow the purpose that a machine, no matter how complicated and how clever, could have, to my mind, isn't equatable. When man has gone, these machines would in essence be purposeless.
I doubt that. I would say, in essence, they would be purposeful.
And there would be, in your feeling, nothing gone and nothing missing from the world.
Well, you mean in the sense in which the dinosaurs are missing?
No, I mean in the sense of something important.
Well, aren't they important? Weren't they important? I mean, there's one thing you could be pretty sure of: man won't survive forever. From all that we know of the sun and of other stars, that would be the most improbable thing. Something else will come.
And in your opinion, it might be something of man's own creation.
Yes.
Well, here's the problem that I'm trying to get at. Here's the thing that I'm trying to get at. You have two grandchildren right there, and I can't see that a machine will ever feel toward any of its
Why not?
creatures the way you feel about them. That's the one thing that I can't get.
Well, I think I could set it up for you, because I'm certain that if I do it, there is a mechanism that can do it. If I can manage to state that in a finite and unambiguous manner, then I think it can be done. And I see no reason why we can't develop a logic of relations in time to come. Granted, it's defective at the present time.
Okay. Oh, yeah.
Hi, Lenore.
Hey, Claudia.
Hi. It's Megan, actually. Hi.
Oh, yeah.
Hi.
Oh, Megan.
Yeah, thank you for this extremely comprehensive talk, and the landscape of how the conscious Turing machine really integrates a lot of the existing, theories that we have and empirical evidence. I was wondering to what extent you think the specific algorithm by which information arises from the long-term memory, from the individual modules into, for lack of a better word, the global workspace or the stage, is the specific algorithm by which there's this specific type of competition based on strength. Is that important? Or are there other algorithms that might do the job there? And how would we ever go about understanding which is the correct algorithm?
Okay, so as I said, we're trying to be simple. That having a valence is one of the simplest measures, plus or minus, and the absolute value is one of the simplest things. And also, as I said, that, in the formal theory, we're imagining all of the processes being potentially very powerful, but not differentiated in terms of their abilities, what they do. And when something happens, and I don't know if Manuel will talk about this, when something happens, for example, when the baby, I'll say it this way. So when the infant CTM, there's a fuel gauge, right? And it needs to be plugged in or get fuel or something, and maybe the fuel's going down or something. Its life is going to depend on that. So that processor that's monitoring the fuel gauge will put in something, a very high thing, help, it's like flailing, like a baby when it's born, just flailing. And then some processor will respond to it, which will start to look for a place to plug in the, whatever, or get the fuel. So these things will evolve. And so the algorithms are not set. They're not set. It's just that they have the potential to do a lot of things. But I'm saying that right now, why not use a lot of things that are already available? So we don't have to start ground up. But if you want a theory and to see how it works, you might do that. But good question. Very good.
Thanks.
So Claudia Passos from NYU. So Lenore, really inspiring talk. So my question was kind of continuation of our conversation about the theories of consciousness and how the model seems to accommodate a variety of theories. But it seems that there are some structures that might be responsible in the model, or structures that where consciousness actually happens in the model. And if there are some structures that are more relevant than others or more required than others, it might be that the model supports some theories more than others. So I was wondering, what is where consciousness actually happens in the model? That means where the magic happens. And if where the magic happens, it might be paired with some theories more than others.
Yeah. So I think it's an ensemble. It's a village. It's federation. There's a federation there of things. Yeah, you take away the predictive dynamics, and it's just feed forward, right? You're saying we don't have that feedback mechanism. You're not going to, there's elements of learning happening here, but I'm not going that direction at all. Yeah, take away the model of the world, and we're back to just the cognitive consciousness. The model of world, at least for us, is the one that we see gives it more phenomenal consciousness. Are there degrees of that? Maybe. So I don't know, and that's a good question for us. We were trying to simplify, and this model is much simpler than what we had 2 years ago, except for the probability. Well, it's more simple with the probability in it than it was before. Yeah, I don't see how if you can help us simplify it, great, and what to take out. And I know that's, yeah, what I see in the theory, there's so many great ideas, but I do see that they, complement each other and in a lot of ways. And if that's the one message that somebody gets out of this from the consciousness thing, that would be a good message, I think. Yes.
Yeah, I thought, that was really, sorry.
Oh, okay. Okay, these are the guys I discuss all the time, but go ahead in public.
Yeah, I was also interested in the philosophical core of your theory. It seemed like the place where the magic actually happens, on your view, is basically, I think you said, a system is conscious because its world model says that it's conscious, which is super interesting thought. That doesn't work for a lot of other things, right? Just because your world model says that you're funny doesn't mean that you're funny. Oh, if your world model says that you're smart or tall or whatever. So how does consciousness get to be? So one way of understanding of you is it's kind of like a bit like the attention schema theory, where you're basically explaining not why we're conscious, but why we think we're conscious.
Okay, well, we would say those are, at least in the model, those are equivalent. But what's really important, it's not that I just think I'm funny, I'm getting feedback from the outside world. I'm not going to just, I might be, that's why I said, the kind of illnesses people have. I mean, I might think I'm really clever and funny and beautiful and all that, but I might not be. And that would be my own delusion, that helps me operate in the world. But most of the model of the world is happening because of your interaction with the world and your interaction. So that's how you're building up your sense of who you are. And I think that, I'm really interested in Claudia's talk about, when the babies sort of develop this more. So I do believe that our CTM has this conscious attention at the beginning, because things are going all over the place. It has to pay attention to, all these things. It doesn't pay attention for long. But then as it builds its model of the world, and I think the theory, the research shows it takes about 7 months to start to develop. I don't know what, I'm waiting to hear your talk on infinite consciousness. But I think it's a little analogous to what's happened with the CTM.
Hi, I love the kind of elegance of this model and how it's compatible with explanations. But I'm curious about how exactly does it connect to the claim that AI consciousness is inevitable? If I could elaborate my question a little bit more, I'm very convinced on the idea that this model and this machine can have consciousness. But I'm curious about, the question is about whether they do have consciousness. And indeed, as the claim suggests, it's a very, it sounds a very strong logical claim that it's inevitable they will, right? And so it sounds to me that this model convinces me as an answer of, if AI is going to have consciousness, it's very likely to look like something, maybe look like that. But I'm curious exactly about the antecedent of this conditional, that is whether they do and whether they can have consciousness. And I think many people who think that AI consciousness is not inevitable is not exactly coming in the algorithmic perspective, but more from some other maybe philosophical or other considerations. So yeah.
So I wouldn't call it algorithmic. I would say computational here. And it's, it's learning, it's changing. It's, it doesn't have a fixed, you do this, you do that, you do the other. So, and that's why I said it would be a mistake to look at what's input and output as the model, because it's what's going on and how it's developing and how it's building all these things is really important to its consciousness. And I think, I'm not saying this is the only model. And if you even go back to Turing has a model, but at the same time, one of the reasons it got to be so important, there were many, many other models of computation that turned out to be equivalent. Turing's is one of the simpler ones. And that gave people a confidence because they happen to be functionally equivalent. They're not complexity equivalent. You know, that's what the, computer sciences, theoretical computer science that brought to the picture, is that you have to take time into account, space into account. Those are going to be important features. So, but I'm not claiming this is the only model. It's a model. And as Dave said, it's sort of based a lot on the global workspace at first, which is based on a little bit of trying to understand human cognition, which actually I realized I gave a preliminary talk a few years ago in Beijing. And after the talk, Raj Reddy, who is my colleague at Carnegie Mellon, came up to me and he said, it's kind of embarrassing. He says, this sounds very much like the Blackboard model we were doing in the 60s and 70s at Carnegie Mellon. And indeed, bars is influenced by the cognitive theories of computer science at Carnegie Mellon in the 50s, 60s, and 70s. Anyway, that's a throwaway interesting thing. But it is based on, I think, trying to understand human intelligence, human cognition, human things. But the octopus is a very good example of, is that conscious? I think there are different kinds, there may be different kinds of consciousness. This is art.
Yeah. Thank you, Lenore.
Hey.
Thank you for your talk. It connects to me with a broader discussion point. Like, indeed, there are many roads that may lead to artificial consciousness. Like, for instance, we are trying to implement attention schema in perceivers with global workspace. That there are different potential ways of attributing self-reflective narrative self. And my question is, like, are we not creating philosophical zombies? And to what extent it's going to become like very hard to decipher if the claims of the machine itself will be hard to disentangle from a pure behavioral point of view, and what it entails from a societal perspective? Because then we're going to have artificial stuff that's going to claim to be conscious, that going to looks like very much conscious, because we're going to plug all our theories to mimic what we know about it. But we won't have a clear delta between philosophical zombies, artificial consciousness, in a sense.
Yeah, well, I think Dave brought that up too, that we're looking for tests of consciousness. And, while we're doing this, so one thing that came out of my view of the CTM is, so the brainish gist or phrase is like a frame in a dream. And dreaming is very interesting because dreaming is very much like, living your daily life, except you don't have the inputs coming in mostly, and you don't have the actuators acting out. So they can be very fantastical. On the other hand, dreaming is very much like your conscious, and everybody claims dreaming is a conscious state. I think that's really generally thought of as dreaming is. So a test for consciousness, at least in animals, might be a test for dreaming.
But for instance, a Boltzmann machine would dream MNIST digits in a sense. So what would be the type of dreaming that is different from internally generating a latent space
well, I said that's a good, that would be a measure of consciousness. That would be, it would seem to me.
Thank you.
Okay.
There.
Hi, Lenore.
Okay. Hey,
thank you so much for your talk.
So you're the person who looked at my brain?
I am the person, yeah.
So we had this wonderful demo the other day at the lab, and I was one of the people who they scanned my brain.
Yes.
I don't know if you could tell whether I had anything there or not, but
there was something there. I can confirm that for sure.
Jen, yeah.
Yes.
Yeah. Okay.
Yeah. So thank you so much for your talk. It was wonderful. The one thing I'm just kind of chewing on or thinking about that I'm wondering if you could speak more to is the specific finite time steps that the model has. And it just had me thinking about like the statistics of the data that this model is taking in and processing within that specific amount of time steps, and whether that relates to maybe the level of consciousness or the measure of consciousness, and whether you've had any thoughts on, I guess, time steps and also the statistics of the data that are being taken in by the model.
Okay, so I don't think I totally understood your question, but because I can't see your mouth.
Yeah, so I guess, sorry, to be more concise, the question is, like with the CTM model, it sounds like it's always, it has a specified number of time steps. And so I was curious your thoughts on the statistics of the data that goes into this model within that specified number of time steps, and whether that might be related to like the level of consciousness or a measure of consciousness, or I guess something like that.
Yeah, I think it's related to questions, more philosophical questions, also like Manuel talks also about free will. It's what you can do. You feel you have free will because it's what decisions you can make within the time you have, right? Whereas many discussions of free will are assuming that time is forever, you have all the time in the world and all of that. So I think the time is coming into it, but I think we have it. I don't think it's special. So we could have the time, I think the way we calculated it with the time steps, it was like a 36 years for the lifetime of this CTM. Not bad. But we can increase the time too. But the point was for this model that it has a finite time. That what it does has to be very quick. Otherwise, it could we want quick computation, things that can happen within its lifetime too. Very important.
Yeah, and I think the last thing was just thinking about like, okay, if you were able to look at all of the data that was fed into this model, is it more impoverished or is it more rich? And does that have impacts on other parts of the processors in the CTM model? Is there some type of dynamic interaction?
Yeah, I think that's related to the LLMs, which one of the consensus that came out of a lot of the talks here was one of the reasons the LLMs are so powerful is that they have all of our culture built in. They don't have to, evolve. So they have all the books in the world. They have all of this information already built in. So I think having the data makes it more powerful. We're right now trying to see how it sort of from very little it would evolve. But I'm saying if you're going to build it, you don't want to build it that way. You want to build it with all the things you have, with all the culture. So of course we want to have lots of chat GTPs or whatever, the newest and best.
I have one final question, which is, if you had access to a neuroscientist, with unlimited resources, Amir, who will do any experiment you can think of, is there one finding that this neuroscientist would provide for you that would make you think that your theory might be incorrect?
So we were talking a little bit about that yesterday with Doris, but I don't know. I was talking to her about dreams, and probably to find out a little bit more how dreams and consciousness are related with these GIFs and the way we frame things in dreams. But offhand, actually, it's a great question, and that's going to be my question for Shiri, is if I had the labs and the talents and the money to look at a question for this, what would that be? What would that question be? Very good. Thank you for giving me the question. And I think it's a great question. And I think there are a lot of people here who can help me with it also, or see questions like this. That would be really good. Great. Yeah, thank you. Great audience.
Okay, fantastic. We'll take a 15-minute break, but I want to remind, if you're a long-term participant and you have an office and you have a key to that office, this is a very good time to go return your key and get your $20 back. Okay, because at lunchtime, the staff will not be here. And at some point they disappear. It's Friday. So go return your key, get your deposit back. Thank you.